Hello friends, welcome to Code Sutra. In this video, I will be explaining the basics of what a trie is, and we will be solving LeetCode problem number 208, that is we will be implementing what a trie is. I will start from the very basic definition of what a trie is and then we go on to solve this problem. So let's first draw an analogy between a binary tree and a trie. What is a binary tree? A binary tree is something that has a left child and it also has a right child. A binary tree is something that has a left child and a right child. But what if we want a third child? Then we can have easily, right? Instead of just having two child, we can have the third child. That is, it will have left child, middle child and right child. But what if we want to have 26 children? Instead of just having one child, two child or three child, what if we want to have 26 children? So is it viable to use child 1, child 2, child 3? No, right? So what we will be doing is we will be using a array of size 26. Instead of individually using child 1, child 2, child 3, we will be using an array having 26 slots and each slot will correspond to one child. For example, this is child 1, child 2, child 3, child 4, child 5 and so on until this will be child 26. So that is how this is implemented. So each trie will have 26 children and these children can be null. For example, here I have just implemented 3 children and all the remaining children can be null. Just like in a binary tree, this can be null, right? So similar to that, there are just 3 children and all the remaining are just null. So that is the definition of a trie. That is, there are, instead of just 2 children, there are 26 children. So, but the next question is, why do we even want 26 children? Right? What is the idea behind this 26 children? The idea is that each position of this array corresponds to the English letter alphabet. For example, this corresponds to A and the ending corresponds to Z and the second will correspond to B, C and so on. So the idea is, if you want to store any word, we can use this data structure. How, we will come to that later. But the idea is, we can definitely store any word here. Say for example, you want to just store one letter here. What do? You want to store the word D here. You go to D here and just say, there will be a new tree node here. That is the child, right? So what do? You create one more thing and you say, okay, I will point this D to the next node. So what does this imply? This implies the first, that is D is not empty. That is, we store the word D just like that, right? What does this indicate? We have the word D. We are just storing the word D. Now let's take a bigger word. Let's store the word and act, for example. How do we store this? We go to the first child. What is the first letter? The first letter is A. So we go to the first slot and we will create a child for that. Why are we creating a child for that? We want to store further letters, that is C and T. So we are creating a child for that and this will not be empty. What is it not being empty indicates? It indicates that A is not empty and we are storing the letter A. So we are storing the letter A and this will point to this particular new child. Now A has a new child that is of length 26. Now we want to store the second letter, that is C. So we go to C. This is A, this is B and this is C. So what do we do here? We do the same thing. We create a child again of size 26 again. Why? Because we want to store all the letters. Again we go to C and we create a child, that is, we created a child and this C is now not empty. This is C, just I am writing these letters, but here letters won't be there. This will be pointing to a new trie node or an array of size 26. Now here we want to store the word T. Where does T come? So T comes here. So again we will be creating a new child. So this will not have anything. This will just be empty. So this is how we can actually store this T. Will again be pointing to this, but this will be empty. This will not be having any letter. So this is how we can store the word act. So just by using 3 arrays of size 26, we were able to store a word act. But if you look here, why do we even need a trie, right? Because we are just storing the word act. We could have just stored it in a string, or we could have even used a hash set to store the word act. But why are we even using this data structure? Now let's get into that. Why are we even using this data structure? See, I won't be writing all the 26. I will just be writing the corresponding letters so that it will be not confusing for me also. It will not be confusing for you also. For example, this is A. What is the next letter that we plan to implement? So this will be corresponding to C. And what will be the next letter? The next letter was T. So what T? And there will be next, that is empty also. Don't forget this, there will be empty also. Here we will be pointing to empty. So we formed the word act. Now we want to implement a new word. For example, we want to create a new word, that is and. So how do we do this? So A is not empty here, right? A, we already filled it. We already have a new word. But in the next, what we will do? We will correspond to this N also. For example, in this array, C is there. Here N will also be pointing to a new trie node. So what is the biggest advantage that we got here? We were able to store two letters in this same array, right? So that is the biggest advantage that we have in a trie. That is, we were able to store it in the same array. Then the next letter, A and T. So the next letter, A and T. Let it come here, A and T. So that's the biggest advantage that we have in a tree. But remember, this T and this T are not in the same trie node. For example, this T and this T will not be in the same trie node. This will correspond to a different. Why? Because this is pointing to a different trie node and this N will be pointing to a different array of size 26. So that is the idea. So why are we even using this data structure? We could have just stored in a hash set, right? Act and. But if you look here, what is happening here is we are just storing two words, right? But if you take a large number of words, for example, if you take any dictionary, for example, there will be very close words, right? For example, we were able to just save a lot of space by using the same array because we wanted to store act and that just have the common initial letter, that is A. We were able to save this data. But remember, in a dictionary the letters are very close to each other, and in real world also, for example, a search engine will also have words that are very close to each other, and hence will also be able to save a lot of space, unlike a hash set. In a hash set, if you want to store act and you will be requiring two different words, but here all you needed was this much space. But if you are storing so much words, you can gauge how much space we will be saving, right? So that is the idea of why we use a trie data structure. Now, okay, we did this. We stored the word act, and now let's store one more word. Let's store the word actor, ACTOR. So A is there, C is there, T is there. Now we just want to store two more letters. Now you understand the advantages of trie, right? ACT, we did not spend anything to store ACT, but for O and R, we are just creating new trie nodes, that is O, and there will be one more that will be corresponding to R. So we stored the word actor also here. So now this will be empty. So let's copy this and try to find a new word. So okay, you have done this. Now I want to find a word ACTO or ACE, right? You go to this and try to find A is there. It is corresponding to child C. It is corresponding to, now let's look here. E, is E there here? Or is E corresponding to a new child? No, right? So the word ACE is not there. So that is how you can conclude. That is how you can search a word and you can also store a word. Now let's try to find out one more word. Let's try to find out ACTO. So if you want to find ACTO, it will say true, right? Because it has A, C, T and O. So we will also require one more parameter, that is will be marking the ending of this. Let's just copy this and let's just paste it here. And so this should be marking. Why? Because we were able to find the word ACTO even if it's not there. So the idea is we will be marking the ending of these words also. For example, we stored the word ACT. So this will, let's mark it in blue. What does this blue indicates? This blue indicates that this word is ending. So when you go to find act, ACT, is T the ending? Yes, T is the ending. So the word act is there. So similarly, R will also be marked with blue. Why? Because that is the ending. Again, here it will be marked with blue. Why? Because that is ending. So if you want to go now and find the word acto, what does it say? Hey, no, we don't have the word acto because it is not ending with O. So that is how we can also store whether the word is there or not. For example, I will show you the data structure of what a trie is. It is just, again, instead of having just one or two child, we are having an array, and this array corresponds to a length of 26, and we will also have one more parameter, that is the end parameter. That is what indicates it is either blue or not. That is will indicate whether this word is ending or not. So that is the idea of a tree. Now let's go into how we insert a word. So the idea is very simple. Similar to we inserted the word act, right? What we are doing, we are taking the character C. Why are we subtracting A from this? Because A corresponds to 0. So that is what we are doing. So now C corresponds to 0 because the first letter is A. And what do we do? If it is null, we create a new trie node. Is A null? Yes, A was null. So we created a new trie node out of it. Then we at C we again created a new node, and we will mark here T as the end. That is, we will mark it in blue. So but for the next word, that is, we want to insert actor, what we will be doing? We will be doing the same thing, but if you look here, until T we will not find anything that is null, because A is there, C is there, T is there. But once you go for the next thing, you want to create a new trie node, and you will be creating a new trie node for C and R. So that is what you will be doing, and that is how you insert. Now let's go on to search. Search will also be the same operation. That is, for every letter you will go on to find. If it is null, you will return false, right? Because say you want to find the word and, you will find A, you will find N, but is D there? No, right? Since D is not there, you will simply return false. So that is what search will be doing. That is, you will be returning false. But if you go here and find the word ACTO, is ACTO there? Yes. But also we will be doing an additional check. That is, we will return the current dot end. That is, if this is marking the end, we will go to the last letter and we check if that is the end. If that is the end, we will return true. If not, we will be returning false. We will just be returning whatever is the ending. Then we have one more parameter that is asked in this question, that is starts with. So starts with is actually similar to search, but the only thing is, for example, if you want to search or if you want to find a word that starts with acto, it need not end, right? So that is the basic idea. The logic is similar to the previous search, but the thing is, instead of returning the end, we will just be returning true if all the letters in S is already there. So this is how we insert, this is how we search, and this is how we find starts with. So the basic advantage of this, or the utilization of this, is we will be using this in a dictionary. We can also use this in search engines, etc. So thank you for watching the video. Please do like, share and subscribe.